Good evening. My name is Cal, and I run a nonprofit coding academy called Cal Academy to empower women and underrepresented minorities in tech. So let's dive into the topic today. I'm very passionate about teaching algorithms and data structures. That's why I'm here. Let's take a problem a day and try to solve that together. So today's problem is about recursion. As students walk into my classroom every day, they always have these fear about recursion. And I'm pretty sure many of you that are watching this video also have the same questions in mind. And primarily when it comes to interviews, there is always this notion of debugging that makes recursion really hard. And so following that through to a program and coming out successfully in interview has been a hard bargain all the time. So I'm going to take a small technique or a small problem here, and I'm going to walk you through both iterative and recursive way. And I'm going to show you how you can map iteration to recursion pretty easily using this concept. All right, let's go to the problem. So here, I'm going to start with this problem with an assumption that you already know a queue data structure. So queue as a data structure allows you to enqueue and dequeue, right? So given those, let's say the question is to just reverse a queue. It's a pretty straightforward question, and many times if you're given a reverse problem, whether it be reversing a string, reversing a queue, reversing something else, majority of the times you can use a stack to solve that problem, because stack is it's a LIFO data structure, last in, first out, so kind of helps you with that. Not to say that that is the efficient way, but it's just one of the ways to help you unblock yourself. So given that, to help you explain this problem, let's say I take another stack, and all I have to do is dequeue the element, push into the stack. Next, dequeue the next element, push into the stack, the next one, push into the stack, and so on until I reach the end of the queue. And then when I'm done, I have to start popping things out of my queue and start enqueuing back into my existing queue to get it back in a reverse form. That is it. That is really the problem. But let's kind of write this both iteratively and recursively so we can understand this mapping. I'm going to use my notepad here to write the code. It's much easier that way. Let me make sure my fonts are bigger. Let's do this. All right. So I'm not going to write code, but I'm just going to write pseudocode first. But for recursion, I can write the code for the time being. But let's take this. In an iterative way, as I just explained to you, the solution goes like this. You first create a stack, right? Let's call the stack as yes, and the queue is SQ, all right? So the code goes like this, which says until the queue is empty, all right? The two things we need to do are, one, dequeue the element from the stack, right? Dequeue the element from the queue, and we need to push it into my stack. Stack yes. All right, that's pretty straightforward. And then when I'm done with that, now until the stack is empty, we need to start popping things out from the stack and enqueue it back into my queue. Is that right? Got it. So pretty straightforward problem, and it is a 2n running time because there are two loops, as you can see, and plus n space complexity because you are taking up a additional stack space here. You got it right? So this is the order of 2n running time plus n space complexity. Now imagine this being your iterative code. Now what I want to help you understand is how do I write this recursively, or how do I even think about recursion? So the nice part of recursion is that, or why would you even use recursion in this space? So really it comes down to this. So you see how you're taking up additional n space complexity. What if I cannot use an additional space, right? And if I have to do this without that, then recursion comes in handy a little bit here because, as you know, we always have a call stack. When we execute a program, we are given a call stack. And if that stack is already there for us, so why not utilize that existing call stack in place of a new stack that we create inside of the program? That way, we are not taking up additional n space complexity. You got that? So let's see how that actually works. So and how we translate that. It's pretty straightforward if you really think in your mind, right? Remember, instead of an additional stack, you're going to use call stack, yes? But the problem with this is, it is a call stack of the system that you will not get access to, which means you cannot do push and pop like the way you normally do in a stack. Instead, push is equivalent to recursively calling the function. You get that right? So for those who do not know recursion is calling the same function over and over again, right, until certain condition is met. So in this case, the push command if I had my own stack, I would actually push the data into the stack. Rather, if I use a call stack, the equivalent of a push command is to recursively call the function, which means you're putting the data again into the call stack, right? So now the pop is equivalent of returning back from the function. So if you do not know call stack, let me just give you a brief or just a quick example of that. Imagine Fibonacci series, right? If you ever wrote a Fibonacci series, if you wrote the Fibonacci series, let me kind of write this in Notepad. Give me a second here. So if you wrote a Fibonacci series, so it looks something like this, very straightforward, right? So Fibonacci of n, and the Fibonacci code would look something like this. If n is equal to 0, or if n is equal to 1, then basically what you're going to do is return the n back. Otherwise, you return Fibonacci of n minus 1 plus Fibonacci of n minus 2. This is a very common Fibonacci code, right? So as you can see, you are starting to use recursion here, where in order to find Fibonacci of 4, you're basically saying I need Fibonacci of 3 and Fibonacci of 2, right? And then to get to 3, you need Fibonacci of 2 and Fibonacci of 1, and so on and so forth, until you reach a specific condition, which is a 1 or a 0. So when you think about this, what really happens in the call stack is when I run this program, let me just bring this to the side. Okay. So when I now run this program, and when I call it for Fibonacci of 3, Fibonacci of 4, let's imagine the call stack and draw it on the whiteboard, right? So the first call here is to Fibonacci of n being 4. And when I enter into this call, imagine this is line number 1. Let me put line number 1 here. This is line number 2, and this is line number 3. And let's make this as line number 3A. So I'll just put A next to it. And this is line number 3B. Imagine this is how your program is coded up, right? So what's going to happen in the call stack is when I enter into Fibonacci of n being 4, the first two lines, the first line is going to execute, the condition is not true, so you're going to right away jump into Fibonacci of n minus 1. So which means the previous call, which is placed into the call stack, is now going to wait in line 3A, while another call is placed into the call stack for n being 3, right? Which means right away this call is going to get executed. So that call comes back in. This condition is not true. So guess what? That's going to also enter into another call, because this is going to now wait in line 3A and places another call into the call stack for n being 2. So you see what's happening? You're recursively calling yourself over and over again. And anytime a call is being made to a function, everything else is put on hold while that call completes and returns back. So this is how you're growing your call stack. You see what you're doing? Every time you make a call to a function, the call stack is growing, right? Whether it be the same function or a different function, that's the general idea. Your call stack just grows. So when I enter into Fibonacci of 2, that also gets in here. This condition is not true. So you're going to make this is going to wait a line 3A, and you're now going to make another Fibonacci call of n being 1. You get that? So now when I'm here, you see this condition becomes true. So there, you now start to unwind, because you're now going to finish this call. This call just popped because you're doing a return. And so it is going to go back to the previous call, returning the value of 1, because we said return n, and n being 1 here. So that call just unwound. So you see what just happened? A call stack is something that you do not have access to, but you have an indirect access to it. And anytime you want to add an element into the call stack, you just have to place a function call. And anytime you want to get the data back from the function, you have to return from the function call. That's it. If you kind of have these two key points in your head, it's easy to translate an iterative code into a recursive code, right? So as you can see here, this call pops back to the previous call, which was waiting in 3A. Now that call moves into 3B. All right. Now what is 3B? You see n minus 2, which is 2 minus 2 is 0. So now, oops, sorry, I didn't mean to do that. So now you place another call into the call stack with the n being 0. And that call has this condition mapped, and so that is going to finish and going to return back a 0 to this previous call. Now you add these two, because it just finished 3A and 3B. Now this call unwinds and goes back with a 1. So you kind of get this idea. So what I wanted to have you take away from this is to use the call stack. And if you want to push an item into the call stack, you place a function call. And when you want to pop an item from the call stack, you do a return. So now, given that, let's go back to our queue problem. So you remember this is our queue, and iterative code, and you saw how we used our own stack. Now I want to write this recursively, and when I write it recursively, remember you do not have your own stack. Instead, I want to use a call stack. And so I'm going to show you how I can map this into an equivalent code. So again, when you do this, kind of keep a call stack in your head. So let me draw another call stack here. So let's ignore this guy, right? So there we go. So let's ignore this, and I'm going to draw another call stack here for this problem. And let's see, here is my call stack. And I'm going to write some code on the left here. So let's call this as, make the fonts bigger. Okay, so now let's call this as reverse queue. Okay, that's my function. And remember, you're given a queue. I'm writing kind of a pseudocode, so don't map this to an exact language yet, but just understand the technique here. So I'm going to reverse a queue, all right? So one of the key things you have to think about recursion is exit scenario. If you forget an exit situation, then your stack overflows, because imagine you're going to be calling yourself over and over and over again without an exit case. So always keep that in mind. The first thing you have to write in a recursion is when you plan to exit out of it. So in this case, if queue is empty, is that right? If queue is empty, what I'm going to do is just return the queue back. Right? There is nothing to do. So imagine a test case when somebody gives you a queue which is being empty or null. I mean, you can check for empty, meaning also for null, right? So either way, I think consider this as a null or empty situation. Then you return the queue back. All right? So now, so let's put some line numbers also, just so that we are tracking towards this. This is line number 1. This is line number 2. Now let's get to the next line. So the next line goes like this. Remember, look at your iterative code. What did we do? We created a stack, and in this case, we are not going to create a stack. So then the second line was until the queue is empty. So that's kind of this, but it's not until, but rather if queue is empty. And then what did we do? If the queue is empty, return. Otherwise, what did we do? We dequeued elements. So I'm going to do the same idea. So let's say I create a variable called d, and I dequeued the element from the queue. So I said queue.dequeue. So if you remember the queue that I had, which was something like 1, 2, 3, 4. So that was my original queue to begin with. So now when I dequeued, my D will have a value of 1. So let's go to the call stack. So let's assume somebody called my reverse queue, this reverse queue function. They passed me a queue which had 1, 2, 3, 4 to begin with. All right. So what did I just do? Is my queue empty? No, it's not empty. So what did I do? In this call, I just created a local variable called D, and I dequeued the first element. There goes my 1, and the 1 goes into my D. You got it? So after dequeue, what did we do in the iterative code? In the iterative code, we said, once I dequeue my element, I'm going to push it into the stack. Remember, we don't have access to stack in a call stack. And what did I just say? When you want to push something into the call stack, you just have to recursively call the function. So there goes. So my line 4 in my recursive code is to recursively call my function. So let me do that. So I'm going to recursively call the function, but what does my function need? The queue. So let me pass my queue in. So what happens here? Remember, I was in this line number 3 when I dequeued my variable 1. Dequeued my first value from the queue, which is 1. Now I call the reverse function. So this line is now going to wait in line number 4 when I made another reverse call. All right. And that call comes in with the new queue. What is my new queue? Remember, 1 is now dequeued. So now my queue variable has a value of 2, 3, and 4. All right. And I enter into the call stack. I enter into the call. My queue is not empty. So I'm going to skip line number 2. I'm going to go to variable 3. Line 3, sorry. And what are you doing in line 3? You're creating a variable. So again, for that call, and there is another copy of variable D now, right? Where you're going to dequeue. So what am I dequeuing? 2. So my variable D now has the value of 2. So what is happening at this moment? So what you just did was you dequeued the element. Now you made another call into the call stack. So which means this is also going to wait in line number 4. Now another call into the call stack is placed with the queue of 3 and 4. And when that enters into the call, a local variable D is created with the first element from the call, so which is your 3. So guess what is happening? Just guess for a minute. So remember going back to our original solution in here. Do you remember when I had my own stack, which was this, I put in values of 1, 2, 3, 4. Do you remember that? Now guess what you're doing with this variable D. You see what you're doing? You're using your own call stack, but even though you do not have access to the call stack, isn't this a nice way you're actually pushing 1, 2, 3 in it, right? So you see how it is translating like the way you wanted by recursively calling it, but using a variable to track what you want. So let's go back and finish the rest. So I'm here. Let's do that. Going back to the spot here. All right, so now I'm back in where I was. So this call just enters into the call stack again. So you are waiting in line number 4. Another reverse call is placed, but this time with the Q value of just 4. And then you go to line number 3, and then this call is going to say, I'm going to dequeue that and store it into a variable D, which I did. Now, and again, another reverse call is being placed. So this is going to be in line number 4. And now you're going to do a reverse, but with the queue actually being empty. So guess what? So we just finished this loop because until the queue is empty, which just happened. So what is now going to happen? Ideally, in the iterative code, we said once it's done, now I need to start doing the other one, which means start popping things out of the stack and putting into my queue. And remember what pop is equivalent to in a recursion. It is equivalent of a return statement. And there are 2 kind of return statements that needs to happen. One for the exit case, which is just here, which is to start unwinding from my queue. From my stack, sorry, call stack. So here it goes. The first statement, what happens is my queue empty? Yes, it is. So I'm going to return. So because you see you're returning a queue, I need to do something. Up until now, I've just been calling, but I've not been storing the value. So let's do this. You see this queue variable that I have in my code already? Whatever return comes out of this call is just going to be overriding my queue. So guess what? This call is empty. It's going to go back to my previous call because you just returned from line number 2. And when you return, the call stack unwinds to the last call that was waiting in line number 4. So you were here. So what are you going to do? Remember, this code just returned an empty queue. So in other words, you're just overriding your queue to hold on to the empty queue now. So this queue is empty. So let me use my eraser here. So this queue is now empty because that's what you got back. Now, what is your code going to do? The code says, what do you need to do? Remember, according to your iterative code, I popped. So the pop is equivalent of this return. Now I need to enqueue that into my queue. So guess what my next line is going to be? If you guessed what I'm going to say, then you guessed it right, which is queue.enqueue. And what do I need to enqueue? The enqueue, the value that I just got from the stack, which is my D. You see my D that I got? So I need to enqueue D back into my queue. So let's put it back now. So 4 is now put into your queue. Is that right? So let's move this around a bit so we can see all of that together. So there we go. So 4 is enqueued back into your queue. Now guess what? I need to return out of this method because you see this method is returning a queue back. So either you return a queue in the case of empty, or when you're done with this code, the last line would be to return the queue back. So let's do that. So this call also, because you just moved from line 4 to line 5 to line 6 now, which is going to return. So this call is going to unwind into the call stack and goes to the previous method that was waiting in line number 4, waiting for this function to come back, which it just did. So remember what you're supposed to do? You're supposed to overwrite your current queue with whatever comes back from the previous call. And what did come back from the previous call? Remember, your queue had 4. So you're going to get back 4 in your queue. And what are you now supposed to do? In line number 5, you are going to enqueue the D value into queue. So guess what? 3 is going to be enqueued into queue. Are you seeing what's happening? You started off with 1, 2, 3, 4. Now you see as you're unwinding, you're getting your 4 and your 3. And when this goes back to the previous call, your queue is now overridden with 4, 3 now, right? And now you're going to enqueue the 2 in there. So now it has got 4, 3, 2. And this finishes, it goes back to the last call where your queue is now going to be 4, 3, 2, right? And the last value is 1, and that gets added into the queue. And you're done. And that is the last call that goes back to the caller. And there they now have the queue, which is now 4, 3, 2, 1. So you see, converting iterative code to recursive code isn't that bad as long as you remember this little trick that when you create a call stack, and if you learn to write your code iteratively, then it is easy to map this code in your head where the push is equivalent of recursively calling the function or the pop is equivalent of returning back from the call. Hope this little function helped you understand recursion a little bit more and make it easier to start thinking about it in the head. Until next time, have a great night.